Right now, sitting out of your driveway, your car isn't actually a machine.
No, it's really not.
Yeah, I mean, without fuel running through its lines, without the ignition active, it is technically devolved into thousands of dormant interlocking mechanisms.
It's sitting there.
Right. And I know that sounds like a bizarre technicality, but today we're taking a deep dive into this fascinating excerpt from a source called Mechanisms versus Machines, defining engineering, motion, and power.
It's a great read.
It really is. And the mission for this deep dive is to fundamentally change how you look at the engineered world around you by untangling these two concepts. Because, we throw these words around all the time.
Oh, constantly. Machine, mechanism, device, gadget.
Exactly. We use them like they're completely interchangeable.
Mm-hmm.
But in the realm of engineering, blurring those terms is, well, it's a catastrophic failure of logic.
It is. It's a fundamental misinterpretation of physical reality, honestly.
Wow, that's a strong way to put it.
Well, it's true. When you look at any complex system, whether it's a spacecraft or just a mechanical watch, you have to separate the intent from the movement.
Right.
Engineers have to isolate the pure geometry of how something moves from the messy, energetic reality of what it's actually trying to accomplish.
The actual task.
Exactly.
Yeah.
If they don't draw a hard boundary between those two concepts from the very beginning of the design process, I mean, the entire system collapses before it even gets off the blueprint. Precision here isn't just semantics. It is the absolute foundation of all engineering.
Okay, let's unpack this. Because the core thesis from our source boils down to one highly specific idea. The difference between a mechanism and a machine is the difference between motion versus mission.
Motion versus mission, yeah.
That is the absolute dividing line.
And we really need to dwell on the word motion first.
Because it comes first, right?
Exactly. It's a prerequisite. Before any mission can be accomplished, before any useful work is done at all, there must be a defined path for movement.
So, establishing the route.
Right. You cannot harness power if you don't first have a highly constrained, totally predictable route for that power to travel through.
Which brings us to the mechanism.
Yes, this is where the mechanism comes in. A mechanism is the foundational building block.
So the source defines a mechanism exactly like this. It's the geometry of movement.
The geometry of movement.
Yeah, it consists of rigid bodies connected together so that moving one part forces the other parts to move in a highly specific, mathematically predictable way.
Highly specific.
Right. And its sole goal, like its entire reason for existing, is just to transmit or modify motion. It does not generate power.
Not at all.
It does not care about the mission. It is pure spatial constraint.
And the term rigid bodies is critical there.
Why is that?
Well, in this specific context, we're ignoring the fact that metal can bend or, materials can stretch over time.
Oh, sure.
We're dealing with pure, idealized spatial relationships. You have these rigid links and you have joints connecting them.
Like hinges and pivots.
Exactly. Those joints dictate the degrees of freedom. They restrict movement in certain directions so that the mechanism only has one possible vector path it can follow.
I think the best way to visualize this is the real-world example from the text, the simple 4-bar linkage on a standard metal folding chair.
Oh, that's a perfect example.
Right. So picture it. You grab the backrest, you grab the seat, and you push them together. The chair doesn't just crumple arbitrarily.
It doesn't turn into a ball of metal.
Right. Because of how those rigid bodies are pinned together, the spatial constraints force the entire structure to collapse along one predefined vector path.
Every single time.
Yeah, the seat drops, the back translates inward, the legs pivot upward. It happens identically every time you fold it. It is a locked geometric relationship.
But notice what the folding chair isn't doing here.
What's that?
It isn't doing work. The mechanism itself is entirely passive.
Oh, because I'm the one pushing it.
Exactly. It merely creates the allowed path. The chair cannot fold itself. It just sits there maintaining its geometry until an external input, your hands, forces it to translate along the single path that its design permits.
That makes total sense. Which brings us to a much more complex example from our source, the slider crank inside a car's internal combustion engine.
Yes, the slider crank.
So you look at an engine block and you see this slider crank mechanism, and its entire geometric purpose is to take linear motion, so the piston sliding up and down, and constrain it so that it translates into rotational motion at the crankshaft.
Up and down is forced to become round and round.
Right. But crucially, if you take that slider crank out and just set it on a workbench, it does absolutely zero work.
Nothing.
It's just heavy, inert metal creating a path. So I was thinking about this. Is a mechanism basically just a physical algorithm?
A physical algorithm.
Yeah, like a set of rigid physical instructions saying, if part A translates 2 inches on the y-axis, part B absolutely must rotate 15 degrees.
What's fascinating here is how accurately that physical algorithm analogy maps to the actual scientific discipline that governs mechanisms.
Oh, really?
Yeah, you were describing pure constraint. And in engineering, the study of these physical algorithms is called kinematics.
Kinematics.
Kinematics is the study of positions, velocities, and accelerations of these rigid bodies. It is the mathematical realm where you calculate exactly where a part is in three-dimensional space, how fast it's moving along its constrained path, and how its speed changes over time.
So it's all about the movement itself.
Yes, but the defining trait of kinematics is actually what it intentionally ignores.
Right, the text mentioned this. It ignores force, it ignores mass.
Completely. Kinematics does not care how much the steel piston weighs. It does not care about the friction between the piston and the cylinder wall.
It just doesn't factor it in?
Not at all. It doesn't care how much human effort it takes to force that folding chair closed. It's mathematically divorced from the forces that cause the movement. Kinematics is pure choreography.
I love that.
Yeah.
I want to stick with that idea of pure choreography.
It works well.
It does. Kinematics is just the dance steps painted on the floor. It
Yeah.
is the how of the movement, perfectly plotted out in terms of angles and distances.
Yes.
But plotting the steps doesn't mean the dance is actually happening.
You need a dancer.
Exactly. You need a dancer. You need energy entering the system, and that crosses the boundary line.
This is the big transition.
Right. We leave the pure geometry of the mechanism behind, and we finally enter the realm of the machine. The machine is the work. It is the mission.
A machine is an entirely different classification. As the analysis points out, a machine is almost always a collection of mechanisms.
The collection of them.
Yeah, it's a scaled-up, integrated system. But the defining characteristic that elevates this collection of mechanisms into a machine is energy transformation.
Energy transformation.
Right. A machine doesn't just move. It takes one specific form of energy, chemical, electrical, thermal, and purposefully transforms it into useful mechanical energy to perform a task or transmit power.
Here's where it gets really interesting, because the distinction seems incredibly razor thin when you are looking at the actual object.
It can be tricky. Yeah.
So let's revisit the car engine example. The engine is a machine because it takes the chemical energy from the fuel, uses that slider crank mechanism we just talked about to guide the motion, and ultimately produces the mechanical power needed to rotate the tires and move the vehicle.
That's the mission.
Right. But wait, so if the slider crank is just a mechanism, what magically elevates the entire engine block into a machine? Is it strictly the introduction of the chemical energy?
What do you mean?
Like, okay, if I put a massive wrench on the crankshaft of a dormant engine, right, and I physically force it to turn by hand, I'm inputting energy, the pistons are moving up and down. Is it a machine then, or just a mechanism I'm sourcing to articulate?
Okay. If we connect this to the bigger picture, turning it with a wrench does not make it a machine.
Wait, really, why not?
Because you're bypassing its designed mission. A machine isn't just a mechanism that happens to have energy applied to it.
Oh, I see.
I mean, you could apply thermal energy to the slider crank by blasting it with a blowtorch, but it's not doing useful work.
Right, it's just getting hot.
Exactly. The elevation to a machine requires the deliberate, designed transformation of a specific energy input to achieve a specific mission.
The intent matters.
Yes. The internal combustion engine is a machine because it is explicitly designed as an energetic ecosystem. It initiates the combustion of chemical fuel, manages the resulting thermal expansion, translates that through the slider crank's kinematic constraints, and outputs torque.
It's all working together.
Right. Without that active energy transformation fulfilling its design task, you're just articulating dormant metal.
Okay, so the mechanism is the conduit, but the machine is the whole energetic ecosystem.
Perfectly said.
The mechanism says, I have the perfect vector path to turn linear movement into circular movement. I just need power. And the machine is the overarching system that says, I have this explosive chemical potential, and I am going to feed it through your kinematic path to propel 2 tons of steel down a highway at 70 miles an hour.
That is the mission.
They are completely dependent on one another, but they are solving 2 entirely different engineering problems.
And because they are solving 2 different problems, they are governed by 2 entirely different branches of physics.
We've got kinematics for the mechanism.
Right. We already established that mechanisms live in the pristine mathematical world of kinematics, the positions, the velocities. But machines exist in the chaotic, forceful world of dynamics.
Right, dynamics.
Dynamics is the study of the relationship between forces, mass, energy, and motion. It brings the heavy hitters into the equation.
So dynamics introduces everything that kinematics pretended didn't exist.
Exactly. When you transition from designing the mechanism to designing the machine, you suddenly have to care very deeply about reality.
The messy stuff.
Very messy. You have to calculate the inertia of the parts. You have to account for the friction tearing at the joints.
Right.
You have to measure the explosive force of the combusting fuel, the thermal expansion of the metal, the sheer torque applied to the drivetrain.
That's a lot to manage.
It is. Kinematics gave you a beautiful, flawless geometric path on paper. Dynamics forces you to push real, heavy, degrading mass down that path without the whole system tearing itself to pieces.
Okay, so to summarize this, kinematics is like watching a silent movie of a moving object, right?
Oh, I like that.
Or maybe even looking at a wireframe CGI model.
Yeah.
You're just watching geometric shapes sliding and rotating across the screen.
Just the shapes.
Yeah, you can measure the velocity of those shapes, you can track their exact coordinates, but you are completely insulated from the physical reality of them.
You don't feel them.
Right, you have no idea if that rotating shape in the wireframe weighs an ounce or 10,000 pounds. You don't know if it's operating in a vacuum or underwater. But dynamics is adding the sound. It's feeling the immense weight of the objects, feeling the searing heat of the explosions, listening to the metal groan under the stress. It's the actual forces.
The explosions and the forces, yes.
So what does this all mean for how we look at everyday objects? Like, why don't engineers just study the whole forceful, energetic reality all at once?
This raises an important question. Why do we artificially separate the motion from the mission when the final product has to do both simultaneously?
Right, because the car has to do both.
It does. But the reality is that the human mind, and even our most advanced mathematical models, well, they require the isolation of variables to achieve precision.
You have to break it down.
You do. You have to master the silent movie perfectly before you can safely introduce the explosion.
Oh, wow.
Think about the mathematical complexity of a running engine. If you try to calculate the thermodynamics of combustion and the material stress of inertia, while the physical path of your mechanism is still flawed or mathematically undefined, the equations just become unsolvable.
The variables would just cascade into chaos.
They would. You have to lock down the geometry first. You run the kinematics to prove, with absolute mathematical certainty, that when the piston translates downward, the crankshaft will rotate without the connecting rod binding against the cylinder wall.
So you prove it in a perfect world first.
Yes. You have to prove the spatial constraints work perfectly in a frictionless vacuum. Only after you have perfected that physical algorithm do you dare introduce the violent forces of dynamics.
That makes so much sense.
You layer the mass, the friction, and the energy transformation on top of a kinematic foundation that you already know is geometrically flawless.
It's like you can't choreograph a complicated dance while the dance floor is on fire and the building is shaking.
That is a very vivid way to put it, but yes.
You map the steps in pristine isolation, you perfect the mechanism, and then once the geometry of movement is locked in, you wrap the machine around it.
Exactly.
You add the fuel, you ignite the chemical energy, and you let dynamics take over to execute the mission.
It is a highly structured method of wrangling physical reality, and it proves why colloquial language fails us in engineering.
How so?
Well, when a mechanical engineer says mechanism, they are explicitly signaling that they are currently only concerned with the constraints, the vector paths, the pure geometry.
They're in kinematics mode?
Right. They are operating in kinematics.
Yeah.
When they say machine, they are signaling a shift to evaluating the energy transformation, the power output, the thermal load, and the ultimate mission.
They're having two completely distinct conversations about the exact same physical object.
Yes.
Which fundamentally rewires how you have to look at the everyday objects around you. I mean, we walk through our days completely oblivious to this sequence of design. We just see a device and expect it to perform its mission.
And take it for granted.
We really do. But armed with this breakdown of motion versus mission, you can mentally deconstruct the engineering around you.
You start to see the dividing lines everywhere. You look at a complex factory robot, and you can visually separate the kinematic path of the robotic arm from the dynamic power system driving the hydraulic actuators.
First, the path. then the power.
First the path, then the power.
You see the mechanism, and you see the machine. So let's lock in the core takeaways from this deep dive into our source material.
Let's do it.
We have separated the terminology. A mechanism provides the path. It is the how. It is governed by kinematics, which is the rigorous study of motion, position, and velocity without any regard for force or mass.
Pure geometry.
Right. A mechanism does not do work. It just dictates how rigid bodies are allowed to articulate in space, like that slider crank just waiting in an engine block.
And conversely, the machine provides the power.
The power.
It is the mission. It is governed by dynamics, which accounts for the messy realities of mass, friction, and force.
The heavy hitters.
Yeah. A machine is a larger system, often a collection of mechanisms that actively takes one form of energy and transforms it into useful mechanical energy to execute a task. The mechanism is the spatial choreography. The machine is the energetic execution.
The motion versus the mission. It is such a clarifying lens to view the physical world through. It gives you a profound appreciation for the sheer mathematical discipline required to design even the simplest objects we interact with.
It really strips away the magic and replaces it with logic.
It does. Well, we want to thank you for joining us on this deep dive. Hopefully, we've broken down some of the assumptions you had about the engineered realities you rely on every single day.
Hopefully.
But before we wrap up, I want to leave you with a final lingering thought based on the strict engineering definitions we just explored.
Ooh, I like where this is going.
If a machine is fundamentally defined by its ability to take energy and do work, well, what happens when it runs completely out of fuel?
That's the question.
Does your car engine temporarily devolve back into a mere collection of dormant kinematic mechanisms sitting in your driveway, completely stripped of its status as a machine, just waiting for the chemical energy that will resurrect it? Next time you see a parked car on the street or an empty folding chair in a room, ask yourself what it really is in that exact moment.